find interesting about Dragon is that it is just...
I'm imagining you'd code up like a script in Python, and then you'd want to rerun that script.
Yeah, right? That's one of the things I find great about it, is that it's just a general purpose programming language, and Dragon is a library with the C library component that you just import into.
It's like the existing kernel GDB scripts themselves are implemented in Python, if I understand correctly.
Yeah. And what essentially happens is that GDB is the like primary, and it links to libpython, I believe, and then
but I'm also like super like I have the muscle memory of GDB and like the commands, and like I want to see the register state, I want to see the instruction I'm at.
Yeah.
So like I want that interface, but I want something that can just generate a pretty printer for me, and I'm going to dump this struct. I'm not going to tell you ahead of time what format it's in. Here's the address of it. You go look up the type information in Dwarf, and you tell me what it pretty printed.
That is exactly what the POC integration in GDB provides.
Cool, nice, yeah.
And for our part, I've thought about. I love Crash. I sometimes put together some code in like a Crash emulation sort of thing. But at the end of the day, Dragon is its own thing. It's not necessarily going to try to have your muscle memory in GDB. But what it is going to do is give you an option to write code that looks kind of like what you would write in the kernel, to go through 3 levels of linked lists to find the structure, and then print the one that matches what you like, and stuff that you can probably do in the GDB Python interface, but it's targeted at that kind of debugging maybe.
I just did a bit of digging around for what it's worth, and while the only comment in GDB about anything like discontiguous stacks is a comment in the Go inferior information saying it splits stacks when they're implemented, there is the Python interface does allow you to implement full unwinders in Python.
Full on what?
Full unwinders. So it looks like you could implement discontiguous frame handling using just or almost just the GDB Python interface without having to hack GDB itself. It's just no one's done it.
Interesting. Funny. So Dragon has various levels of extensibility like that, and the unwinder support is something that's only extensible at the C level, as far as I know. But other things, for instance, type formats, you can actually, similar to Dwarf, you could implement support for a type format to add type finders that can look up, say, what is struct, task struct. If you had a pickle definition for it, we could write a Python implementation of that and load up a pickle and get that type information. So similar for finding objects, finding variables, you can extend the Dragon side of things in interesting ways from Python or C, but I don't think stack unwinders are there. They can always be added, Any feelings about?
Does any of you actually have the use case for this kind of programmable debuggers? Because that's something that
and I was going to echo I work with KGDB a whole lot, and I was going to echo the GDB stub. Using just GDB stub, I think, would also solve the KGDB issue for working with Dragon. But at least for the poke stuff, that it sounds interesting. Although I will say I tend to use the GDB scripts normally because they just magically are there when I build the kernel and use them. And I do wish they did more. And so I don't know, the poke stuff does sound interesting because I do often end up, while debugging, I have a linked list and I want to follow the linked list, and there's just at least no way that I know of to do it well. And so I write really complicated GDB expressions where I calculate offset of myself in GDB and then subtract it and do next myself to iterate through linked list. And it's all doable, but it's super complicated. And
yeah, usually I give up.
No, it's not that bad. Once you start learning to use temporary GDB variables, it's okay, and you know how to implement offset of it is not that hard. But yeah, it
I am too stupid for doing programmable stuff with GDB, not with the Python interface that I have never used.
The Python interface or GDB, at least for me, is super weird and confusing.
I don't speak Python.
Oh, okay.
I'm sorry.
So definitely the linked list iteration thing is something that Dragon is exactly suited for. It's the sort of thing that someone has written all of the linked lists offset of stuff for you, and it knows about the types, and it would just go ahead and do that for you without needing to know stuff. But it's still, if you don't speak Python, it could be a frustration.
Only if I am forced to.
Fair enough.
Hang on.
Oh,
Say it on the mic.
that was that. Poke support and Dragon is what I just heard from Nick.
Yes, poke support for Dragon, I think. Bring the warring camps together.
Well, I mean, there's no war here as far as I'm concerned. But what I'm excited because the use case that Jose is talking about with Poke for payloads, you know, you've got an ELF file. I'm learning, you know, Poke from you here and continuing on because I want to be able to dump an ELF header really fast. And you know, that data type isn't available in Dragon, and I would love to just pop open Poke for that. There's probably some room for collaboration, but again, as Dragon is a, you know, extensible, or is a Python library, call out to Poke, shell out to Poke, or take the buffer, write it out to disk as a file, and suddenly you have an ELF file you can pop Poke open with. Maybe it's not the workflow everyone loves. There's obviously a room for improvement always, but
some misintegration will be not that difficult to do in the same way we integrate Poke in GDB, we can integrate it in Python as well.
And a Python Poke implementation could take all of those nice Poke definitions for TCP headers, for ELF files. You could load those up into Dragon with the right plumbing code. So that this is all hypothetical here. I shouldn't say that it's implemented or anything, but those are all options, and they can unify in interesting ways.
So I wanted to ask about the different trade-offs that GDB and Poke make versus Dragon. For example, when it comes to CPU and memory usage, right? Because sometimes you want to use these debuggers in production, right? And perhaps you don't mind that it's a bit slower as long as it uses less memory. For example, I know that Dragon does like a heavily parallelization with OpenMP, and it does a lot of indexing, but I don't know, how do they compare in terms of memory and CPU?
Well, I can reply to that very, very quickly. Poke is extremely slow at the moment. And the reason for that is that it's very new. And we have been focused in the last couple of years in functionality. Because, there are certain things, some of the things that Poke does, we did not know how to do them because there was nothing doing those things before. And we did not even know if it was actually possible to do it. And some of this stuff is actually not that clear. So Poke is very slow at the moment, yeah. We will release Poke version 3 at the end of the summer, hopefully, which is better. But actually, I designed the compiler in a way that what is now the backend is going to become a middle end. Right? But yeah, it will get faster. But right now, no, yeah, and for sure it cannot compete with the Python implementation. No, for sure not.
To come at that, I certainly can't speak from the GDB Python perspective, so I don't want to really make any comparisons. I don't know that we have benchmarks or something like that. But to your point, yes, Dragon, one of the things it does is it parallelizes dwarf reading and loading with OpenMP, because that can get really slow if you're looking at a ton of modules and VM Linux and all of that jazz. And that is really noticeable. And I can say that Omar, it's funny, in our pull requests, he'll tell me about the milliseconds regressions on loading dwarf, on loading debug info. So he knows about startup time regressions, and he focuses on that, at least in terms of startup, how to get from not running to debugging a program with full debug info. That is something that he focuses on. For other things, you know, you have the Python implementation. So whichever Python implementation you have, they keep getting faster generally, and then a fair amount of it is written in C. But, that I don't know where else to go on performance, but those just pointers. Yeah. That helps.
Thank you.
One question to the both of you. Which use cases do you see Dragon and GDB Poke used most in? So in the distros, we usually do dump debugging, but the way I understand it, Dragon is more designed for live debugging, or at least the original goal was more for live debugging. Is there any limitations towards dumps or other use cases you think the tools don't cope good with?
Okay, so dump versus live. I mainly use Dragon myself for dump debugging rather than live debugging. I think it might be the reverse for Omar or for others who are using it, because one of its strengths, as you said, is kind of run on a live kernel and extract some data out of the kernel that you wouldn't find in a proc file system or something like that. But I can't, in terms of limitations, honestly, Dragon is going to be faster on a core dump, much faster, because proc kcore is pretty darn slow to read from versus a file that you can load and read very quickly. It supports make dump file formatted crash dumps. It supports ELF formatted crash dumps. You might run into some issues with the more exotic crash dumps. If you have a hypervisor memory dump, you might need to do some massaging with VM core info or something. And we're always looking at those GitHub issues because we want to support more of them. But that would be the first limitation that springs to my mind with dumps. As far as user space, though, they're generally all ELF files, and they're all pretty easily readable by Dragon. So 10 minutes. And anything you want to add from the GDB poke side?
Whatever GDB supports,
Okay.
it's supported.
Maybe when there's no other question, one for Dragon. Do you support cross debugging, also cross NDNS?
So it's cross-platform, you mean? Yeah.
Yeah, cross-platform or cross-arch, cross NDNS especially.
Yeah. So Dragon is implemented to, so it has basic architecture support for a few architectures, at least ARM 64, x86, x86 64, and I think several others. But and it's also implemented with an eye towards byte ordering, things, those sorts of things that are going to affect your debugging. That said, several items aren't going to be as useful on another architecture. You might not have all of the helpers that you do on x86 64, but if you have a Dragon compiled on x86 64, it should be just as functional at reading an ARM 64 core dump as one compiled for ARM 64. So for the cross debugging side of things, yeah, it should work on that. Like things like the orc unwinder won't work nicely, of course, because there's no orc, but
Sure.
yeah, and we're working on those architecture differences as well. We've trying to improve. I know there are some folks at Oracle too who are really interested in getting everything as good as possible on ARM. So
As long as I'm generating insane ideas, I might point out that if some of your problem with cross debugging with Dragon is that you can't execute the assembler at some different instruction set, it was always QEMU in emulation, so you could call out to that.
yeah, this is true. One thing that GDB does, and Dragon will get there with live user space debugging, I think, and we'll probably, if there's a GDB stub option, you'll probably have that as well for kernel stuff, that you might be able to do some limited starting and stopping, but it's not there now. And so we haven't even started about the idea of emulating instruction sets or anything. I wouldn't expect to see that sort of thing.
Reverse debugging too.
Reverse debugging.
Yeah. Well, if you are going to support like executing instruction forward, you should support executing backwards too, like GDB does.
Yeah, so we're definitely thinking a lot more along the lines of a crash dump where you have your memory, you have your data that you want to extract, or a live system. Similarly, I know that there are plans and roadmaps that include the starting and stopping, but I don't know that we're ever going to be doing things like reverse emulating or forward emulating. GDB is great for that. Okay. Yeah, unless we have any other subsystem specific ideas, things that people are looking for that they find that are missing with Crash, missing with GDB. All right. Yeah, I guess we're done. Thank you.
Thank you so much. Okay, I guess we'll be back in 7 minutes with our next speaker.
Ulster, do you have any stickers? You said you had some stickers, right?
Yeah,
Yeah. We need a dragon sticker.
only one black left.
Okay. I can get a white one.
Well, I have white, black on white, and red on white.
I think I will get black and white, if that's okay.
No, black and white.
Yeah. The most common one. Oh, thank you. It's kind of cute.
The last one. Yeah.
Because the YouTube people were complaining the YouTube live stream went out. So I think if people were watching on YouTube, I think they got. So I ran out and went to find James Bottomley and it's
Yeah.
it's back online and it came up back like almost halfway through kind of thing, but I think
it was more of a you want to be here.
either way, I think like the live stream, I don't think they're gonna post like the full track. I think they're gonna be recording the actual thing and they're gonna slice those up and then publish those as vlogs on YouTube later. So I'm not worried about like the talk not being recorded or anything like that. I think it was more of like if someone was tuning in on the live stream, there were two live streams. There was one directly from like someone could join the room. There's three live streams. So someone could join the meeting. Someone could join like there's a people who run like a view only mode, and then some people were on YouTube. So people just like 4 minutes. We'll start.
This PCI. I don't have it.
What we'll do is just make sure you see one. And then we'll change it. And make sure you introduce yourself when you start, and then if you want people to interject during the talk versus questions for the end, maybe and then I'll try to give you things up with like 10 minutes, 5 minutes.
last one I used was just this USB usable.
About the case when you have given them and return, and then can you just give that return? So
Yeah.
and it's like a fashion of a fashion. Well, in practice, you don't see cases where something is being translated.
I will show you. It's not complicated.
Hey, folks, I think we'll be getting started with the next presentation.
Hello, everyone. My name is Indu. I've been working with a colleague of mine on designing and implementing CTF frame. And today I want to spend some time going over just the overall idea behind CTF frame and then go onwards to discuss some use cases that CTF frame may find in the Linux kernel. So since this is a shorter presentation, I have about 25 minutes. I think I do not want to get into the details of the format, but I do want to go over just some key ideas to give you enough background so you can judge the value proposition of CTF frame format. So CTF frame format is a very simple format for stack unwinding, right? And it is plain vanilla stack unwinding. There is no state recovery. So all it allows you to do is, given a PC, you can just walk the stack, and it helps you recover just three minimal variables here, which is CFA, FP, and RA. And it is a format that you can use if your use case is fast unwinding. And so we posted patches on the binutils mailing list a few months ago. And right now the status is their V6 patch, V6 version, they have been reviewed. But if you go look into those patches, there is an unwinder based on CTF frame. And you'll be able to tell that the unwinder is simple. And the reason it's simple is because the format itself, the encodings and the representation is simple. So these stack offsets that you need to walk the stack, they are encoded directly in the format. So there is no stack machine that is necessary to unwind, or there is no complex expression encoding that you will need to, implement in your unwinder if you want to do the unwinding on a, online unwinding or offline, either way, right? You don't need any such support. So since I cannot get into the details, I still want you to get a flavor of what CTF frame format is. I think I will make these two statements. Disclaimer that these are oversimplifications, so there are pitfalls here. So for those of you who know dwarf EH frames, dwarf EH frame, inside a dwarf EH frame, you have these dwarf opcodes, which an unwinder will need to execute. And once the unwinder has executed these opcodes, it gets the stack frame offsets, which you use to unwind. Now, contrast that with CTF frame. So what I like to say here is that think of CTF frame as interpreted EH frame information. So, which means that these stack offsets are encoded directly in the format. So given a PC, you get these offsets to recover CFA, FP, and RA. Now, for those of you who, well, I think most people would know also ORC here. So ORC is CTF frame is very similar to ORC in principle. I do have a slide later on. They are a bit unorganized at this time. But as I show that slide, I think you'll be able to relate to CTF frame better. This again is one of the things that I think we should keep a mental note of, which is that CTF frame information is not tied to CTF type debug information. If you want to unwind, there is a new section that we added, which is .ctf frame. And that's the only section you need if you want to unwind. You do not need to go to .ctf section for your basic plain vanilla unwinding needs. So yeah, this is the slide. So this essentially shows you the, what should I say? This shows you the key data structure in which you keep the unwinding information. For those of you who know orc, this is similar to the orc_entry data structure in orc, right? So this data structure shows you, so the syntax is, shouldn't say weird, but the syntax is based on in poke. So, and I have cheated a little bit. I'm trying to compress a lot of ideas here, thoughts here. So there are 3 flavors of CTF frame. So that's why I use these slashes to say there is CTF frame address 1, address 2, and address 3. Basically, these are 3 encodings. Each of these encodings, the only variation between these 3 encodings is the amount of bits that you need to encode the addresses. So if a function is 200 bytes, you need a lesser size of encoding for just specifying the addresses in that function. So that's what this exploits, right? So there are 3 different variants of CTF frame, CTF FREs. And essentially what CTF FRA gives you is, it tells you, given a PC, these are the offsets that you need to unwind from this PC, right? So there is a union here which says that, the union just says that either it will be an offset of 8 bits, all these offsets are going to be 8 bits, or all these offsets are 16 bits, or all these offsets are 32. Again, the second set of offsets is related to how much stack you have been going, within your function, how much of the stack you have been using. And the first, the address stuff, is basically how big your function is. What is the range of the PCs that you're interested in unwinding for this? For this function, what is the range of PCs? That's it. So now I'm going again. So this is all the details that I had to give about the key ideas in CTF frame format. So let's just put it all together. And so CTF, there is a new section that we have added. This is .ctf frame. It's a loaded allocated section, and it will appear in a segment of its own. So it is easy to start unwinding. And the support has been added to GNU Toolchain. The support at this time is in bin utils. We do, and we will add a little bit of support in GCC, which will be only, which is just like a wrapper putting everything together. So it will emit a .cfi section directive and pass it to the assembler. But at this time, yeah, you can use the assembler and pass ---- gctf frame, and it generates the CTF frame section. So again, I think too much details maybe is not necessary. You guys can take a look at the patches, and we can also talk later. So support-wise, yes, you can generate CTF frame. The linker will try to merge these CTF frame section from input files. And what else? There is a library. There is a libctf frame that you can include to, if you want to use CTF frame sections, you can use this library to decode and find information from the CTF frame section. Size, yeah, I think this is just to give you a flavor, and I do make a disclaimer here that I do not intend to show that this is lesser than EH frame, and it says something around that, but it is just to show that. So initially my concerns were that CTF frame could, because this is interpreted dwarf EH frame, the size could go higher, much higher than EH frame, and maybe it's not in a very reasonable ballpark, but given the optimizations that we have put in, the good thing here is that it is still in the reasonable ballpark, and that's the only message I want to send across, and nothing else. EH frame in general is quite compact, right? So this is also a good sign that at least it's in the reasonable ballpark, the sizes of CTF frame. That's it. So now let's just put everything together. So I have come across So we know that for unwinding, we do have dwarf EH frames. And I have come across not just one, but at this time, I have a count of 3 unwind formats out there. 2 of them are open source, and 1 of them is not. I don't know much of the details about the non-open source one, thankfully. So the 2 which are open source, right? Both of them have the reason why they are in place, and the whole reason why they exist is because people and applications have the need to unwind without EH frames for many different reasons. So one of the arguments against EH frame is often that I want an unwinder which is less CPU intensive, less memory intensive, and that's one of the reasons why people want to drift away from EH frame for unwinding. And the other reasons sometimes are just that the unwinder in itself becomes, I think it's related, yeah. Basically, they want a simple unwinder and a fast unwinder. And so then putting everything together, right? All these on the left-hand side are the requirements for unwind formats. So asynchronicity is very important. So let's look at that first. EH frame is great at that. CTF frame, I do want to say that it is almost asynchronous. It is not completely asynchronous. And if you want to get in details, I do have a slide later on, I can explain. But I do want to add here that it is very close. It is closed. It is quite, it is almost asynchronous. And for the application-specific formats, I think it's a tricky thing here, either to say yes or no, because just representation-wise, I have seen that they are asynchronous, but because of the way they are generated, you often do not have the complete unwind information, which then makes it asynchronous, right? So what is the commonality in all of these application-specific formats that I have seen is that they're not generated in the toolchain. All these applications tend to have their own generation logic, because of which the solution now becomes asynchronous.
I'm sorry, just a quick question. I'm not actually sure what you mean by an asynchronous format. Would you mind explaining just a bit?
Sure. So asynchronous means that you can unwind, given any PC, you can unwind from that PC and get a backtrace. Now, whether it is reliable or not, you want to be reliable as much as you can, but it just means that given any PC, you can unwind.
Got it. Thank you.
So yeah, the other desirable requirements of any unwind format is they be fast and the unwind info be small. And CTF frame fares well here. Simple, small unwinder, which is very true for CTF frame at this time. And we hope it will be. We want to put as much effort as we can in making sure that remains, because that's the whole reason for existence for CTF frame at this time and should remain so. CTF frame is not application specific. As I see these application specific formats, there is one thing or the other that makes them very specific to that application. And it's not a bad thing, because if you have an application, you know exactly that there are some requirements or quirks in that application that you can exploit to keep your metadata small. Sure, why not, right? But if you want something to be done, like supported in toolchain and something like that, you need to be inclusive of everything. So CTF frame, yes, is not application specific. ABI and architecture support, CTF has support for 2 set of ABIs at this time, the AMD 64 and the AAPCS, well, AR64, the 2 ABIs, big endian, little endian. And I think that's it. So I hope at this time you have a high-level idea of what CTF frame aims to do and what it offers. So the questions that I had for the audience here are, well, many different dimensions. One of them is I wanted to explore if there are people interested in seeing if CTF frame can help out in the Objtool for org generation. So I know from previous LPC and this year talking to people that there are issues around control flow reconstruction, especially on AR64. So the value in this would be that, whatever be the control flow, I'll just finish this thought. Whatever be the control flow, since you have the unwind information generated by the tool chain, the information is there in the unwind format. So if you use something like that generated from the toolchain, then you do not have the need, I think, as I understand it, you do not have the need to reconstruct the control flow. Yes.
Yeah, so I was going to say on ARM64, the big reason that we need to do this at all is for asynchronous unwind. And as I understand from what you presented just now, we don't have enough information there to do some of the asynchronous cases that we care about, because one of the big problems we have is disambiguating when the link register contains a legitimate value, when it duplicates what's in the current frame record pointed to by our FP, and when it's the only thing that should be used. So that's the major thing that we need to do on ARM64, and if we can do that, we can get asynchronous unwind generally. There's a few special cases that we have to handle for trampolines and so on, but I don't believe that this as is helps there, and we would need some more information for that.
No, CTF frame will just do it for you out of, well, the current implementation will do it for you. What is not, so this is what I say here. So the offsets tell you, if there is an offset in the FRE, it tells you that this is on the stack. And if there is no offset, then it is right, it is 100% right to say that it is in the link register. So the information is encoded such that if there is an offset, it has to be on stack, because the compiler sees it as it generates the code that it has saved it has saved the link register either on stack or it remains in the register. So the CTF frame will give you that information. I think, yeah, for AR64, this is a relevant slide. This is the reason why I say that this is not fully asynchronous. Now there are two, left and the right. So let's focus on the right one. So basically, what I'm not sure right now is that AR64 also has these instructions called BLRs, right? So when you return the link register is not just LR, it's some other register, right? So that's something that CTF frame does not encode. CTF frame, the encoding itself, this is implicit in the format that if it is a stack offset, it has to be on stack. If it is not, it is LR and no other register. So that's why I said it is not fully asynchronous, because that information is not encoded in CTF frame.
Okay, so BLR is only used for forward edge calls.
I see.
We do use RET. RET can take a general purpose register as well, other than the LR. Compilers don't currently generate that, but we do use that in a few trampolines today, like F-trace trampolines and so on. But those could be special cases.
Okay, then it's fine. So that's one of the reasons why I said it is asynchronous. So glad to know that it is not a common case, at least for the code generated by compiler, correct?
Yeah.
And the second case is that there is the CFI negate array state. So this assumes that in the addresses that you're encoding, the upper bits are, well, this feature says that in the upper address bits, it's some sort of signature, right? It's not complete address. So that needs to be encoded in the format that if you're reading some like PCs, you need to be sure that this just the upper bits are, addresses. So that encoding we don't have right now, which essentially means that if there is any function that uses these CFI directives, you will not have CTF frame unwind information for it.
Okay, is that just saying, as the slide says, that a pack instruction has been used effectively, that it's been signed with?
Yes, if these instructions are being used, then the compiler will emit the CFI negate array state accordingly.
Okay, but we'll
right?
still have the other information saying the offsets and so on, because currently
Yes, yeah.
our current unwinder
So,
completely ignores this, and it just strips out the authentication bit and assumes that the address is correct, because we can reliably do that at least. So it might be that we can just ignore
I
that.
see. Yeah.
So I had another question is, how do you see this being used at all for user space stack unwinding instead of for using frame pointers?
Sorry, the question is whether I see value in user space unwinding using CTF frame?
Yes, so basically getting a stack trace from in the kernel from a user space program that does not require using a frame pointer, but can use the CTF frame information instead.
Yeah, why not? Is there...
It would be extremely useful to have that
Yeah.
in the
Yeah.
kernel.
And since the support is in Toolchain, I think that's the first step. Once it's in Toolchain, then people find it easier to use, and then the format evolves. And, things get simpler if it is in the toolchain. So yeah, and that's one of the things I actually wanted to talk about, also asking people if they see value or if this is a use case. So sure, all you have to do is, yeah, use the available toolchain to generate the .ctf frame and
Yeah, as long as there's a kernel unwinder, I'll make sure
yeah,
every binary
there
has the
is-
information.
Yeah, we have an unwinder solution provided, but I think there's some little work that we would also like to do, as in the unwinder, it uses some more mallocs than necessary, so there's some work needed there, but it is usable. It's
So for instance, various architectures in the kernel, they have a choice between unwinders and they have some trade-offs. And so it might be perhaps an interesting exercise to demonstrate the capabilities of CTF, to implement an unwinder for the kernel and post patches that do so, because it's one thing to say like, well, it should be simple to implement an unwinder, and then you sit down to do it and you're like, oh my God, there's so many corner cases. What awful corner of hell have I backed myself into?
Yeah, I think,
right.
yeah.
And then that gives the community the ability to measure and assess the trade-offs themselves. And then that helps with further tool chain adoption if someone's able to say, you really want this format because of reasons X, Y, and Z.
Yes.
Yeah, so on the matter of doing user space undefined from kernel space, currently for x86 we have the option of frame pointer, or just plain copying a bunch of the stack and hoping user space can sort it out. On return to user space, which would be the ideal point to unwind the user space stack, you could do a CTF unwind provided that the task you're trying to unwind has the CTF information mapped and you can find it. So that might be interesting to do, but it's not entirely trivial to pull off. I mean, at the return to user space point, you can take page faults. So the CTF information doesn't need to be loaded in memory, but it does need to be mapped.
Yes, it does need to be available, and yeah, mapped is what you say, yes. If the program is active, I don't see why not, right? Yeah.
Final comments or questions?
So just one last question. One other issue for unwinding we have on ARM64 is PLTs, or procedure linkage tables. Basically, when branches are out of range, we have to go through those, which get generated by the linker. I'm assuming that the CTF information is only generated by the compiler, and so we would have nothing for those. Is that correct?
No. So here, the flow is like this. So the compiler emits CFI directives. The compiler would not emit PLT at this time. Then comes the assembler, which reads these CFI directives and generates EH frame and also now CTF frame. Then comes the linker, which will link these CTF frame sections and generate CTF, final CTF, or link in these EH frames and generate the final EH frame. Also, the linker generates the PLTs. Right, so we added support for x86. We have the support that it will the linker will generate CTF frame entries for PLT. For AR64, I still have to work on that. But for x86, the linker will generate CTF frame entries for PLT.
Okay.
CTF frame information for
it would
PLT.
be very useful to be able to identify PLTs specifically for our unwinders, because there are some cases where we do not follow standard calling convention, will not have, our return address will not be in the LR at the instant we go through that PLT in some cases. So being able to identify the PLTs with our unwinder, we can do a special case, would be very useful.
I don't think I understand that perfectly. What does it mean to identify the PLT?
To distinguish it from a regular function. So to
Right.
just have some Boolean property that this is a PLT generated at length time. We can discuss this afterwards.
Yes, sure, yeah.
Okay, let's have a round of applause for our speaker. Thank you so much.
Thank you. I do want to take a moment to just say that I did want to get into even these things here, which is that if you have any ideas on how to improve CTF frame section, be it for reliable backtraces and other use cases that you may have seen in the kernel, yeah, get in touch with us and I'll be happy to take discussions later on. Thank you.
introduce yourself. If you want people to interject questions first, maybe stay still at the beginning. And I'll come 10 minutes, 5 minutes, 3, 2, 1. And you can take it away.
Okay. Hi, I'm Josh Poindbuff. I work for Red Hat. I'm on the core kernel team. Work on a variety of security and x86 related things. Spectre, speculative execution type mitigations, live kernel patching, kernel unwinding. But today I'm going to talk about Objtool. So this is not really a big presentation. It's hopefully going to have some discussion. So if you have questions or comments, feel free to jump in. And unless we start running out of time, because I do need to get to the problem statement kind of halfway through. So is there a keyboard shortcut?
I think the arrow keys work. Otherwise, you can click at the bottom.
Yeah, okay. All right. So Objtool is a kernel-specific tool. It reverse engineers the control flow graph of compiled objects. It performs various validations and modifications to those objects. And in general, the overall goal is to improve the robustness and security of the kernel. So it has several features. The only ones I'm going to discuss here are the ones that are related to this control flow graph, which it reverse engineers. So the original feature that inspired Objtool was this first one, which is stack unwinding metadata validation. Is basically validates frame pointer rules with the goal of making live kernel patching safe. It relies on reliable stack tracing. And then this work was extended to add the orc unwinder. So as it's very similar to what Indu presented with her CTF frame. It's a simplified version of the dwarf unwinding. And then there's a few other features that also rely on this reconstructed control flow graph. One of them is SMAP validation. This is Intel supervisor mode access prevention. It's a security feature that the CPU provides. It prevents the kernel from accessing user space memory. And what Objtool does is kind of validate that this feature is always enabled except for user copy to user, copy from user. Otherwise, this feature's always enabled. And another feature, so both of these last two features were added by Peter Zylstra. Also, Thomas Gleixner worked on this last one too as well. No-inst validation. What this one does is it ensures that in certain critical sections of code where you don't want unwanted function calls, profiling, or instrumentation being added in the function. So this just kind of validates those rules and makes sure that there's no surprising function calls being inserted in certain places. So I've gotten this question a lot, like why does Objtool reverse engineer the control flow graph of the compiler starting from the object? So the main reason is related to the kernel has ASM, a lot of custom assembly and inline assembly that does a lot of interesting things. And those are really kind of blind spots for the tool chain. as far as understanding the full control flow of the kernel. One potential solution for much of that is manual CFI annotations, and we used to do that before we had live patching, but we had a lot of problems with those, keeping them correct, and they were always kind of half broken and really difficult to maintain, especially with a lot of the creative uses we have with assembly and inline assembly. So we eventually kind of gave up on that approach, especially when we needed live patching, and Objtool has helped with that. So, and other reasons why we need this control flow graph is these other features I mentioned, the SMAP validation and the no-inst validation, which are very kernel specific, and Toolchain doesn't really understand those things. So Objtool has actually been doing this for maybe 5 years or so, and it's pretty good at it. It's very good at it, but it has to hack around certain things. It has trouble with a few places. One of them is the detection of no return function call sites. So after the call site to a function that doesn't return, the compiler optimizes out the instructions after the call, and this kind of throws Objtool for a loop, because it really kind of needs to know that. So that's one challenge, is the detection of such no return functions. Another challenge is the detection of jump tables. So the biggest example of this would be this like C switch statements. The compiler often converts or compiles such switch statements to like an indirect branch and a jump table. So it's like a list of text addresses that the indirect branch will jump to. So again, Objtool has a hard time kind of reliably reconstructing that flow. And we have it working. It's been working for several years, but it's like pattern matching. It's really kind of a hack, and it really only works for x86. We tried it on ARM64, and it was even much harder. So it's probably impossible from what we could tell. So that's pretty much the problem statement. Basically, I'm proposing to help solve this issue. I propose that the compiler can give us some kind of hints to kind of annotate the jump tables and the no return functions to kind of help us recover that control flow information. So I sent out kind of a more detailed proposal to the Linux Toolchains mailing list. This is kind of a very high-level overview of what I sent out. There was a lot of discussion about details, but this is really kind of just the important thing for this discussion. So, for example, there's a fannotate no return flag, which creates an ELF section. It's not allocatable. It's just for other tooling to read, and it references all the no return functions and call sites, or their call sites, depending on how we implement it. But so Objtool would just read this, and it would help it kind of fill in the gaps. And then similarly, there'd be an F-annotate jump table flag, which creates an ELF section, describes all the jump tables in the file, kind of tells Objtool where the indirect branch is associated with the jump table and where the jump table itself is. So if there's more details discussed on the mailing list, but this is pretty much at a high level what I'm proposing. So
I was going to say, for the no return case, for ARM64, this is not as useful as some other options. One of the things I would really like to have instead of this is just to have the option to have a trap instruction placed immediately after any call to a no return function, because that also means it will catch problems at runtime if we have a no return function that actually returns somehow. And it also means that we can guarantee very trivially that every return will return to the middle of a function rather than the next one. It gets rid of an edge case where the next instruction is in another function. And I think on that thread, someone said that feature does already exist. So that might get rid of that problem by construction. And I imagine that it will only be a small amount of additional instructions in the entire kernel.
yeah, that idea was brought up with the trap right after the call. And the one thing I'm not clear on is if Objtool has enough information to figure out the reason for that trap, because there's other reasons for traps. So it's not clear to me yet whether we would still need this annotation, but yeah, that is a useful feature to have that. Yeah.
But like, if we could get a well-defined set of traps that use for different things, I think that would help.
Yeah.
Do we have any compiler folk around? Because one fear I would have with the F-annotate jump table data is that the format of the jump table and the exact structure and the way it's used could change over time. Because you could have relative jumps, absolute jumps, all sorts of things.
Yeah, I mean, there was some talk about future-proofing the format of the ELF section. We could either, like, there was some suggestion that we could point directly to the jump table, or we could kind of rewrite it in a way that's easier to read and also maybe more future-proof because it doesn't depend on the jump table being in a certain existing format.
I did a brief search for prior art for jump tables. I suspected this is a similar issue to a utility in the LLVM tree called Bolt. It does post-link optimization. And sure enough, on AR64, they also had heuristics and imprecise heuristics for trying to determine the jump table problem. So I'm guessing they may be extremely interested in potentially working together on something that is maybe code base agnostic and could solve the problem for both us and them, kind of thing. So I'm happy to, we had the presenter Bolt at LPC last year, virtual. So we could probably, reach out to them and maybe at least at the very least discuss the problem and try to figure out, what might a solution look like that is, makes everyone happy, kind of thing.
Yeah, that's a great suggestion.
And I think another talk earlier as well today alluded to no return functions being problematic, kind of thing. And so to me, it's kind of, the question that I have is like, is this something that should be encoded in ELF somewhere in a symbol table, in a custom section with a custom format? Should it be in dwarf, kind of thing? And I think, to me, the question is always, surely other people have a similar problem, and how can we make solutions as generic as possible so that they solve our problems in kernel space, but also, someone in user space surely has the same issue, kind of thing like that. So.
So on that no return thing, right? So the thing that we talked in the morning was more on what the user has stated in their high level language. So which means that if they say this is a no return function, then you want it to be reflected somehow so that ABI analysis like tools can use that information. But I think the requirement or the complete set of no return functions, or the requirement of Objtool with respect to no return is wider, correct? You just don't need the Objtool just doesn't need only the ones that have been marked as no return using an attribute by the user, but also the ones that the compiler deems as, or the compiler later identifies as no return, right? So
That's
this
right.
is wider, and which needs something more than just annotations that we were thinking in the morning, which could be in an else section or maybe in debug info. Yeah, that part is still.
Yeah, that's
Yeah.
right. Compiler just doesn't only depend upon the no return annotation. There are
Yes.
other, heuristics or whatever that it uses to decide that it knows that this function doesn't return. So sometimes it's kind of an implicit no return attribute. So
Yeah, the typical problem with Objtool has is that it can't tell the difference between a no return and the compiler just figuring it should stop code gen.
it should stop what? I didn't catch the end of that.
Code generation. Sometimes the compiler just gives up and stops code gen in the middle due to various compiler bugs, or it wasn't.
Yeah, we have found a few bugs where compiler just gives up and just moves on to the next function. But yeah, we've reported, yeah.
I think a lot of those have been undefined behavior in the source code,
Yeah,
and those end up being turned into unreachable blocks, and that kind of shreds the control flow. Those get rotated to the end of the function, and then we potentially have a jump that looks like a fall through to the next function. So like even the discussion on the list about like, well, could you turn those into trapping instructions? Yes, but it may not disambiguate the no return function case, because you could still have UB in your function that leads to a similar case, right? So you'll get the trap that has nothing to do with no return.
Does that actually matter? Because what we actually care about isn't that the user explicitly annotates it as no return. We just care that you can't return it. You can't forget the trap. So I think that distinction might not matter for the use case of reliable stack trace, which is why we have this stuff in the kernel.
that's true. That's true. So maybe that, yeah. It would be, Objtool's analysis would be slightly different because it would actually execute the UD2, but it would stop there because it would see, oh, we're trapped. So the end result is basically the same.
Like all the fall through warnings that we've gotten from this from Objtool, like we are able to avoid those. I'm not sure that's the correct term, but like internally we have like an internal compiler flag for it. So it was interesting to see the discussion on the list that said like, no, there is now a flag for it kind of thing, because it makes it so that I can give it a name and wrap it easily. Because I've been very strict about avoiding like compiler internal flags in kbuild, because like I don't want to be mucking around with the compiler internals kind of thing. So I think that's something I can wrap in Clang probably pretty quickly and have that at least. But I guess I don't know if there's we do that and then no return problems go away, or if there's more to the problem kind of thing. But maybe that's one of the two, at least pretty quickly.
Okay, any,
So what is problematic about jump tables?
repeat?
What is that problematic about jump tables when it comes to reconstruct the flow control graph?
So Objtool reconstructs control flow by following the branches.
Yeah.
And it tracks, it's like, for example, the state of the stack at the time. So the jump table, it needs to know if it follows that branch, it expects the same stack state there. But if it kind of falls through and doesn't follow that branch, it might get there a different way with a different stack state. So
Okay, I see.
Yeah. Okay, thank you.
Okay, thanks again for all of our speakers for this block of talks. We'll have a 30-minute break and we'll be back for our final talk of the track. Thanks, everyone. Okay, are our remote presenters online here? Do we know who's going first in the lineup? Joe? Okay. Hey, Joe, are you online? Are you able to say hello to folks?
Yeah, you hear me?
Yeah, sounds great.
And Nick, what do we do? Do we all switch on the webcam before time, or?
If you don't mind, why don't you all just leave your webcams on, if that works?
Let me go try this.
Yeah, hello. And then in the bottom left, you'll see the plus, and you can say take presenter mode. And then that will give you the ability, you can use the arrow keys, or at the bottom it says slide left and right. And then, whenever you're ready to hand off, Mark, are you going to be doing a part of the talk as well? Perfect. Yep, that sounds great. And then if you're presenting slides, you hit plus and say take presenter from here. Okay. Whoever's going first, just make sure you introduce yourselves.
Well, I'll introduce myself from here and then say, hi, I'm Mark Rutland. I'm at ARM, talking about this control flow integrity stuff. Joe, do you want to introduce yourself?
Yeah, sure. So I'm John Moreira. I work for Intel. Spent some time in academia doing control flow integrity kind of research, and that's it.
Peter?
I'm Peter Zelstra. Most of you know me. I also happen to do this.
And Sammy?
Hey, I'm Sami. I'm in the Android platform security team at Google.
Cool. I'll leave it to you, Joe, for now.
Okay, thank you. I just close the door in a sec. I'll be right back, because dogs. Have fun. Bye.
Can the dogs present, Joe? Is that an option?
That would be fun.
Okay, I'm sorry. I'm in. Dogs got crazy. So, yeah, I'm here with Peter, Mark, and Sammy. We're going to talk a little bit about how we're planning to do the control integrity kind of upstreaming and the kernel. It's mostly like actually Peter, Sammy, and Mark doing the work. I'm just here like annoying them. So I guess I have to start with some disclaimers from my employer because I have to put this on the slides. So be aware about all of these. And now let's talk about why control flow integrity. So as most of you know, if you do have like code written in C, you're going to end up with a lot of like memory safety bugs. So things that allow like an attacker or like a malicious user to corrupt your memory. And by exploiting this sort of like bugs, an attacker might be able to override a function pointer or maybe like a return address on your stack. And using that, he might be able to do what we call the control flow hijacking, which is basically like taking control over the control flow of your application and doing like a bunch of stuff that you might not want he or she to do. Because of this kind of problem, it's like sort of like a very old problem. There are like a bunch of mitigations in place. So first, for example, you have like write, XOR, execute kind of mitigation, which says that when you have like a writable page, this page should not be executable. And by doing that, you basically like are preventing an attacker from injecting code into your application memory. You also have like stuff like ASLR, which randomizes the data structures and the code within the application memory and makes it like harder for an attacker to figure out where a pointer is. So he may not like be able to override it or even like a structure in the code that he might be willing to reuse for his attack and stuff like this. And well, when these came in place, attackers came out with different methods for attacking. So they start like using code reuse. So you might have heard of like return to libc attacks or memory disclosure attacks that are like bugs that allow an attacker to figure out the memory layout in your application. So he basically like might be able to bypass ASLR with these, so figure out where like is the stuff that he needs to override or to point to. And in the kernel context, you also have like the return to user attacks, which basically the attacker would manipulate memory in user space and then just like reference this memory from the kernel space. And because of things like this, mitigation basically implemented this concept of strong address space isolation. You might have heard of SMAP or SMAP. which is CPU's extensions that basically prevent you from dereferencing user space memory from the kernel side. And by doing that, you basically like prevent an attacker from just manipulating your memory in user space and then using it in his or her attack. Because of stuff like these, people came up with these ROP, JOP, or COP kind of attacks. ROP stands for return-oriented programming. JOP is like jump-oriented programming. COP is call-oriented programming. It's basically like indirect branches being exploited to allow control flow hijacking. I like to call this whatever op or WOP because, I mean, in the end, it's just like an indirect branch that is being used to launch the attack. And what the WOP basically consists in is reusing kernel code or the application code already, which is there, using this concept called gadgets. And a gadget's basically like a small instruction sequence, which ends with the indirect branch being used to launch the attack. And because the attacker might be able to manipulate the memory, which is used to define the target of this indirect branch, the attacker may just like, start like chaining these small sequences. And when they end with the branch instruction, they're going to jump into the next gadget and then jump to the next gadget and so on. And by doing this sort of stuff, the attacker might be able to achieve this meaningful or malicious computation. So imagine, for example, that he might be able to disable SMAP, for example, and then from there, once SMAP is disabled, he might be able to just manipulate user space memory, and from there, like launch a new attack and stuff like this. So it's really like kind of complicated sort of attack to mitigate. And because of these sort of attacks, which are like kind of like randomly, not randomly, but arbitrarily chaining these gadgets into your application memory, then came this, people came with this idea of like control flow integrity, which is basically confining the indirect branches of your application to previously computed locations. So you build like a control flow graph of your application, and you say, yeah, every indirect branch is only supposed to go to this set of specific targets. And by doing that, you're like not enabling him from or her from indirectly calling random pieces of code and like chaining them at will in a way to achieve the malicious computation. When it comes to CFI, you have like basically two big groups. We have what we call coarse-grained CFI, where you have like valid and invalid targets mostly, so you don't have like subgroups for them. So if you have an indirect branch, this is specific indirect branch is allowed to go to any valid target. So you only have like valid and invalid targets. You don't have like a classification for them. And it was shown by researchers, academia mostly, that this sort of like mitigation is insufficient because, for example, imagine that you eventually might need to call a function indirectly. And then if you just call this function indirectly in a different context, you might be able to, still attack the system. It would be the case, for example, with a disable security feature kind of function. So if it eventually needs to be indirectly called, then it would be callable from any indirect branch in the application. And well, this still like poses a problem. Then people came with a more strict sort of policy, which is the fine-grained CFI. And the idea is basically you cluster the targets in groups. So now an indirect branch has a specific subgroup of targets that it is allowed to go to. So we're not like able to point to all the indirect branch targets from one specific indirect branch target. And this has shown to be like much more reliable in terms of security than doing coarse-grained kind of thing. Slides not moving. Okay. So here we're mostly like talking about forward edge, fine-grained CFI. The current implementation that we're discussing, it's not like really focusing on return instructions right now. So we're like focused on doing like a function pointer protection, so indirect call protection. And as some of you may know, defining the possible targets for a specific indirect call is kind of hard. So it's an undecidable problem from the computation perspective. So you can't like really just go in your source code and figure out what are like the precise set of functions that should be callable from a specific function pointer. You cannot like really do that by just doing analysis. So we need to come up with some heuristics for doing that. And there's this idea of like doing pointer and function prototype matching. It actually like comes from a paper from 2005 written by Abadi, which is the very seminal paper on CFI. And the idea here is that if you ever declare the pointer in C, you know that you need to put a prototype on it. And if you ever declare the function, you definitely know that you also like need to have a prototype for it. So if you have like prototypes for both of these, so before you actually execute an indirect call, just make sure that the pointer being used in this indirect call has the very same prototype as the function which is being called. And by the way, we're basically like clustering based on the prototype of functions. This approach is like rather old. It's been used on other existing solutions. So have GR Security Wrap, Clang CFI does the same thing. Microsoft XFG does the same thing too. So it has shown to be like quite useful and safe to some extent. Currently, in the Linux kernel, this is what we have and what we are discussing for next steps. So first you have internal direct range tracking. This is a coarse grain scheme and it's hardware based, so it's like a CPU extension. You have ARM BTI, which is also coarse grain and also like based on the hardware extension from ARM. And you also have like a Clang CFI on ARM. This is already supported. This is already there. And it's fine grain software based CFI. So basically just use Clang to emit specific code constructs to enforce the CFI. And the idea is to replace these with KCFI as soon as possible, I guess. As said, I mean, we're currently like working on a few schemes. First one is KCFI, which is mostly being written by Semi by now. And it's fine grained, it's full software based, so it's been implemented on Clang. And I think that it already landed on Clang, and I think that it's almost there for the kernel support. And we also have this idea of like doing fine IBT, which is basically reshaping the way that IBT is used. So it's like a, let's say, IBT hybrid approach. So it uses the hardware extension, but extends it a little bit with some compiler instrumentation to make the actual IBT fine grained. So it's sort of like hybrid approach to achieve the same kind of security that KCFI provides with a few advantages. Now I'm gonna head over to Semi to talk about his work on KCFI.
All right. So as mentioned, ARM64 at the moment supports Clang CFI, which Google is currently shipping in Android kernels. However, this CFI scheme was primarily designed for C++ applications in user space, which makes it not quite ideal for kernel use. Basically, it uses jump tables for validating indirect call targets, which means it has to change all function pointers to point to a jump table. And this is a problem in cases where we need the actual function address instead. And additionally, each kernel module has its own jump table, which means that this breaks cross-module function address equality, which causes all kinds of fun problems. Clang also requires link time optimization to be used with CFI, so the compiler can determine all the call targets. And that significantly increases compilation times and can also increase binary sizes, which makes it undesirable in some cases. So that brings us to KCFI, which is a new fine-grained CFI scheme that we contributed to Clang recently. And it should be in the upcoming Clang 16 release. And it avoids all the aforementioned issues with the Clang CFI and therefore making it more kernel friendly. KCFI is extremely simple. It consists of the compiler emitting a type hash before each function entry and then before each indirect call, a check that reads the type hash and ensures we're jumping to a function with the expected type. Should be noted that reading the type hash obviously makes this scheme incompatible with execute-only memory, should the kernel support that one day. If there's a type mismatch, KCFI always traps and leaves it to the kernel to handle the error. Right, can I? Let's do the next one. So because of the design, KCFI requires some minor changes to some assembly functions. Specifically, any function that's indirectly called from C code must be manually annotated with the correct type hash, or indirect call checks will fail. What makes this slightly more complicated is that the type information is only available in C, but the annotation must happen in assembly. So to make this easier, we changed the compiler to emit a KCFI type ID symbol for every address taken function declaration in C translation units. That means that when you link the C translation unit with the annotated assembly code, it can conveniently resolve the expected type there. We're introducing a macro that makes adding this type information easier. Basically, it consists of replacing the sim_func_start macro with sim_typed func_star in the function definition. The only catch is that you have to ensure that there's always at least one C translation unit that takes the address of the function.
Just to add to that, because of other reasons for linking with modules, we normally have to do that anyway. So I think that should be okay.
Yeah, it shouldn't be a problem, really. All right, and let's quickly look at the actual instrumentation that we generate with KCFI. You can see here, the target function bar has a preamble that contains the type hash. On ARM64, we simply have the 32-bit hash value, while on x86, we emit a function symbol and embed the type hash into an instruction. This is primarily to avoid confusing Objtool and other parsers with random bytes, but also to enable fine IBT patching, which we will cover later. On the caller side, the compiler emits the exact same check sequence for each indirect call, with only the registers possibly changing. We can clobber caller saved registers here because the check is immediately before the call, and any registers that were used were already saved. On x86, we negate the expected hash value and load it into the R10 register, and then add the hash we read from the target. And if the result is not 0, we trap. Since x86 has variable length instructions, it's important that we don't accidentally end up embedding the full hash into any of the instructions, as that would create a valid indirect call target that an attacker could potentially exploit. And that's how we ended up with this specific sequence after some back and forth. So if the check fails, we're going to hit the trap. And since the kernel doesn't otherwise know why we hit the specific trap, the compiler generates a KCFI traps section, which contains the locations of all the traps in CFI checks. The trap handler can then use the locations to see if this was a CFI failure or something else. On the ARM64 side, the instructions are all 32 bits long, so we don't have to worry about accidentally embedding the hash in them. The check here uses 2 temporary registers, reads the target hash into one of them and loads the expected hash into the other one, and then traps if they don't match. And unlike on x86, the trap instruction includes an immediate value which tells the kernel that this was a CFI failure. And it also encodes the registers we used in the check, so the error handler can conveniently report the actual values without having to decode the instructions themselves. And this also means that we don't need a KCFI traps section for ARM64. By default, KCFI failures result in a kernel panic, but the kernel can also be configured to use permissive mode, where it continues execution after a type mismatch, only printing out a warning. Version 5 of the KCFI series was posted to LKMU last week, so please take a look if you are interested. And that was all I have. Do we have Mark next to talk about BTI?
Right, yep. So as mentioned earlier, ARM has one of these coarse-grained forward edge control flow integrity features called branch target identification, or BTI for short. It's mandatory in ARM v8.5, so not in any hardware you have in your hand at the moment, but some point soon. It's ARC64 only, so it only exists for 64-bit code. There is no equivalent in 32-bit. If you want to look this up in the ARM architecture reference manual, look for this feat underscore string. It's what our architects want to call this. The extension adds new instructions called intuitively BTI. These are encoded in a reserved space of opcode which behave as NOPs on existing hardware, so you can build binaries using this and they'll just work on existing hardware. What these do is that they enforce indirect calls to these addresses land on these specific instructions. So BR instruction, a branch register, which is like a jump on x86, must land on a BTI J or JC. The J and JC there stand for jump and call. So it's just saying, you know that this thing is jumped to. BLR, branch and link register, which is our call instruction, can only land on a BTI C or JC. They can't land on a BTI J. So you place these throughout your binary in the correct places, and only the correct instructions can land on these. In addition to this, there's a new attribute in our page tables called the guarded page bit, or GP. To enable these checks, that bit needs to be set. So if for any reason you have a mixture of code where you can't apply this check, you can just disable the feature on a per page basis. Can I move to the next slide? Can someone move to the next slide? I don't have control.
If you hit the plus in the bottom left and then say take presenter.
It's fine.
Yep.
Yep. So how this works in practice is you get a new compiler or a contemporary compiler, and you pass it some flags, which I forgot to put on the slide, but what it will cause the compiler to do is to place a BTIC or JC in the function prologue at its entry point, depending on whether it might be called directly for other reasons. The existing auto-ASP instruction, which is part of pointer authentication, is compatible with BTIC, so we don't need to add 2 instructions there if you're already using that. And in addition to that, the kernel obviously has to go and set the GP bit on its own code page tables. When you have that, enforcement is ensured. So it works with Clang version 12.0 plus. We had some unfortunate issues prior to that with linker stuff that doesn't matter. And it is present in GCC as well, but as of a few weeks ago, we've identified an issue where we've had to temporarily disable it due to GCC forgetting to place a BTI in certain functions that are callable from a separate section, which could be placed too far away, go through a PLT, and the PLT uses a BR rather than a BLR, so it can't land on a BTIC. That's going to get fixed soon, but the fix isn't present just yet. And so with that, I think I'm done. I think it's Peter next.
Let me go try and advance this thing. Take presenter, and I click.
You can try the plus in the bottom left and then say.
Oh,
presenter.
sorry. No, there was one more slide. I've forgotten. Sorry. So this is what it looks like. In your caller foo, we just have the exact call sequence you have today, BLR, branch and link register, where the address is in the register x0. If a function might be called indirectly, so the compiler is aware that the address is taken or it's like exported or whatever, then it places one of these 3 instructions early in the prologue, and then the rest of the sequence is exactly as is today. And for a function that's only called directly, so via branch immediate or branch and link immediate instruction, it doesn't need to do anything special. It's just exactly as is today. You don't need to put a BTI because those are not checked. Because we know at build time, the compiler didn't call the wrong function. Sorry, and now you can go, Peter.
Hooray! That's me. Yeah, so Intel has a similar thing. We call it indirect branch tracking. You'll see it's the same 3 letters, but permuted differently. It's part of CET, Control Flow Enforcement Technology. It's one half. The other half is shadow stack, as Case alluded to earlier today. We too have new instructions, also taken from an instruction space that was previously not. We have 2. end branch 32, end branch 64 for respective code types. The hardware raises a exception if you do an indirect jump or call and do not land on the end branch thingy. Unlike ARM, and this is how I ended up here, on x86, it's also specified that the indirect branch execution stalls speculation until an end branch is encountered. Unlike ARM, where they fill with page tables, we have a no-track prefix. If you add that prefix, IBT gets disabled for one thing. Luckily, you can enable or disable the no-track prefix independently of IBT. So for the Linux kernel, we disabled that. No-track is invalid in kernel code. Objtool actually checks for this. If it finds an instruction with a no-track prefix, it will yell. A consequence of this is that we had to disable jump tables for x86-64 because GCC could not enable indirect branch tracking and not emit no tracks for jump tables. Luckily, jump tables were already disabled due to red pooleans. Red pooleans make indirect jumps very much more expensive, and therefore jump tables are generally not worth it. I think AJ fixed GCC. We now have another option so that we can do IBT and jump tables and not have the no track, and then it'll sprinkle end branch throughout the function. I'm not sure what the Clang state of that is. So for now, we still do the no jump tables, even if you do not use red pooleans. It's something that needs to be sorted out. Right, so the compiler, a recent enough compiler can emit end branch instructions. We had to fix up the eBPF JIT to also emit them. And I started coding this before I had hardware. So I used Objtool to find me all the locations that should have end branch and didn't. I mean, the compiler generally puts in enough, mostly too many end branch instructions. But all our inline assembly also needs end branch. So I wrote an Objtool thing to look at all the code references, every code location that has its address taken, and has a few other conditions, like is the first instruction of a symbol, should have end branch. We have annotations for the cases where it shouldn't be, and all that. But that works. We run this Objtool pass at the VM Linux stage, so it's an LTO-like run. This means we can find superfluous end breaks. Unlike ARM64, where they have the PLTs, we generally have a big enough immediate space to not need PLTs for the kernel. Hooray. Therefore, we can actually remove end branches. So that we do that. I scribble it with a 4-byte no-op. The end branch instructions are 4 bytes. If we were to fix up all the immediate jumps and calls to land at the instruction after end branch, we could scribble it with a 4-byte trap. And that would mean that even on non-IBT enabled hardware, an immediate jump to a function that shouldn't take it will trap. But finally, IBT and KCFI will fix most of that. So that's not really that important. I think Zwau once did an LLD variant that does the same through LTO for Clang. The ceiling, that is. This is what it looks like. You do an indirect call or jump, doesn't really matter. You need to land on the end branch, otherwise you get a CP trap. And then, like Sami said earlier, will either warn or just burn your machine. A consequence of this, if you look at the address taken and the non-address taken thing, is that the Fantry call will not be at offset 0. And this was a lot of fun because ftrace and everybody else assumed that on x86 the Fantry call was at offset 0 for every symbol. So that took a bit of wiggling around to fix all that. But yeah, we got that sorted. And what's up? You want to do this again?
Sure. Yeah. Feel free to jump in if you have like any comments or something. Well, we'll talk a little bit about fine IBT, which is a way we find out to be able to make IBT actually fine grained. So if you paid attention to what Peter said, I mean, you have the end branch instruction. End branch instruction is basically a valid target for any indirect branch. And what this means that you end up with a coarse-grained control flow graph. And we don't want that because, well, coarse-grained is not good enough for preventing control flow hijacking attacks. So we actually like use the compiler to extend the way that IBT is emitted in the code and make it like fine-grained. We call this fine IBT, but it's actually like just a silly name for a compiler instrumentation. Like we said, I mean, IBT will do the caller side checks. So if you have like an indirect call go into a non-end branch instruction, you're gonna like crash. And fine IBT will basically augment the prologue. So it's actually like a callee side check for doing the prototype kind of checking and hash matching. And you can basically like just go to the direct calls and augment the operand there. So you just add a little bit, few bytes there to just skip these checks from when you were doing a direct call, right? So you don't like get the checks for direct calls because this wouldn't make sense. This is not exactly how we came up to implement this in the kernel. We'll get there, but this was like basically the original idea. I need to get control again. So the way we were thinking fine IBT is basically like to hot patch it on top of the KCFI instrumentation. So basically you get KCFI, you compile your kernel with KCFI, and that's the instructions that the compiler are going to generate, like on your left side of this snippet here. And then when you're basically booting your machine, the kernel will just look if IBT is available. If that's the case, it will just like basically hot patch your kernel memory to do the fine IBT instrumentation, and that's basically it's gonna go to the what's like on the right side here. So on the caller side, we're basically like replacing that move minus hash with like a sub and a few bytes. In this case, 16 bytes. The idea here is to, if you're doing an indirect call, you are gonna like actually target a few bytes before the function entry point, and then you just put like the hash you want to match into R10. And then on the callee side, you have the end branch like 16 bytes before the function entry point, which basically allows the call to go there. And then you just sub the hash from R10. And if the result of this operation is 0, which basically means that the hashes are matching, you just jump to the function entry point. Otherwise, you are going to hit the UD2 instruction, which you like trigger sort of like a CP and whatever. One interesting thing about this fine IBT instrumentation is that it doesn't depend on memory reads like KCFI will do, and this actually like has some interesting effects to the CFI scheme in general. So first of them, I mean, like Peter said, I mean, IBT will confine the speculative execution to the coarse-grained CFG. So if you have an indirect branch, it's mandatory that this indirect branch will land on an end branch instruction, even speculatively. So you're not like able to just go out like trying to mistrain indirect branches to go somewhere arbitrarily. You need to end in an end branch. But then when it comes to fine IBT, if we take a look, I'm gonna like move a slide back here. If you take a look at the instrumentation, you have like a conditional branch over there. So the JZ. And this conditional branch will actually like have a speculation window. Yet the resolution of the target for this conditional branch only depends on instructions that are not doing a memory read. And because of that, because you were just like putting an immediate into R10 and then just doing a sub from R10 from another immediate, the target resolution for this conditional branch is like quite small. And because, I mean, the resolution is like, it happens kind of fast within the CPU. And because of that, the speculation window is kind of small. And what this means in practice is that it is like kind of rather hard for an attacker to place a speculative execution gadget that might be executed within this this speculative window, and also like is not like kind of matching the hash. So it like to some extent actually also enforces the fine-grained CFG to the speculative execution behavior. And this like of course makes it like the IBT hardening a little bit further strong. Some other like important characteristics here is that it makes FineIBT compatible with stuff like execute-only memory. So if you have been following the mailing list for a while, I mean, I think that a few years ago, Rick Edgecombe submitted some patches for doing execute-only memory using MPK CPU extension, which is a rather cool mitigation, prevents like sort of like different classes of attacks. And because we don't like need to read from executable memory to do FineIBT, we might be able to make these two things work together. And also, I mean, because we don't have like memory reads, it's likely to show better performance than KCFI. We never made these measurements, and this is like a super bold statement. Cache is super efficient for KCFI. I know it because I made some measurements long time ago only on KCFI. But still, I think that not having the memory reads kind of like should be better. Peter, you wanted to jump in?
Yeah, I wanted to mention Spectre BHB, so that FineIBT with the speculation hardening is a valid defense against Spectre BHB. Whereas currently, I think the recommendation is to run with Red Pauline, even if you have enhanced IBRS available. So in that respect, it would be a performance improvement as well.
Okay, thank you. Yeah, I mean, thank you for being more specific about it. I really don't know much about speculative execution attacks, so good to get better insight on that. Another thing that I constantly think about when it comes to comparing FineIBT with KCFI, and this is like really something up to discussion because I don't have like a closed idea about this, but I have like this understanding that FineIBT should be less disastrous when you need to relax things. So imagine you have like a function pointer in your source code, and this function pointer is like a void star type. So you're going to call functions that don't have like a matching prototype. And because of that, you basically need to not do the CFI policy enforcement. And with KCFI, what we would need to do is to basically not do the instrumentation of the indirect call. On FineIBT, it would be like a little bit different. So you would still have the IBT enforcement, right? So you still like have the coarse grained CFG below everything. And then on top of that, I mean, all you need to do is to relax the function itself and not the function pointer. And what this means is that because you know the function that you're relaxing. So let's say, because you know that this function is like harmless, so it's not like a disable secret feature kind of function. You know that it is like safe to relax it. Otherwise, I mean, if you need to relax the indirect call, so if you need to relax the function pointer, you can basically like reach any point in the memory space from there. So you have like a relaxed indirect call. You are now able to call, let's say, disable smap function from there, and this is like very disastrous because you're enabling important secret feature to be disabled and so on. So just because you have like this sort of like more fine-grained control over what you are relaxing with FineIBT, I think it makes like a little bit better from the perspective of security. Like I said, I mean, like up to discussion. Yeah, go ahead.
So I think the most prominent no CFI indirect call we have is the jump into BPF, if I'm not mistaken. So that thing is no CFI, right?
Yeah, that's correct.
Okay, yeah, so yeah, I think that a long time ago we went down kind of fixing the void star function pointers in the kernel code. I remember that I think I had like a patch with keys like a long time ago for the cryptographic functions in x86 because you would have like a bunch of callbacks there. But I think that these are like mostly fixed now. I'm not sure how's the state in kernel code, but thank you for the update on BPF. So yeah, I mean, no CFI functions are like rather problematic, I guess, and you wouldn't like need to have this relaxed for fine IBT. So yeah, I think that these are like all the slides I prepared. Maybe we should jump into discussions if people have questions, suggestions, or anything.
I have a question. Earlier today, Kees mentioned that this work was coming along for Clang and said that it would be good if GCC were to also do this. Is anybody actually actively looking at this, doing an implementation for GCC? For KCFI, that is.
To my knowledge, no one is working on GCC.
Okay. Yeah, then the only comment I have at this point for the KCFI patch set is that I think the preprocessor symbol is Clang CFI or CFI Clang or something like that. Should we change that to be KCFI or something and not mention Clang? Or do we want to do a mass rename once GCC grows this feature?
I am personally flexible here, so happy to hear any thoughts people may have.
Yeah, the room shows it. Ah, perfect. Can you guys hear us now?
Yes.
Okay, sorry, we've been muted and trying to talk a few times up until this point. Things generally don't matter. Could we go back one slide just before the questions?
Absolutely.
Because I was going to say that on the existing Clang CFI scheme, one of the reasons why we've had to disable checks is because of like calling into assembly functions in weird address spaces and so on. With KCFI, we can actually have those checked because we can put the type hash before those functions in assembly. So actually, we should get better protection there, and we shouldn't have much reason to have to disable checks at all. So I'm hoping for ARM64, we will not have to disable any checks. Sorry.
I was gonna say I haven't looked too closely at the patch set, but around Peter's point about renaming the symbol, I think something that Sammy did for LTO was have the LTO symbol signify that we're doing LTO, but then have the choice be around the compiler, and the symbol that was actually selected by the user was Clang. And that would only be set or only selectable if Clang was being used. That way you have the separation of the feature versus the compiler that's being used. So something that might be helpful for us to look at is where are we setting, Clang CFI as the config symbol, and seeing if we can separate that from the feature being enabled and stuff that's going to be more generic that GCC might be able to take advantage of, and things that are more implementation of Clang based that maybe want to be surrounded by a Clang CFI symbol.
Yeah, that sounds entirely reasonable to me.
Any other comments or questions for our speakers?
People tentatively raise their hands but quickly drop them.
Here we go.
It's not a question, but mostly thank you all for doing this work. It took a lot of coordination, and it's awesome.
I'll point out that there are many others doing the work, some of whom are here.
Right on. Thanks everyone for coming to the table. A lot of work goes into this. So hopefully we can provide safer kernels for everyone. Okay, if that's all the talk, all the comments and questions we have, let's have a round of applause for our speakers. Okay, I guess we'll say some closing words or something, huh? All right.
Well, we have the umbrellas.
Okay.
So if there are any speaker who has not an umbrella and wants one, come here. You get it.
Yeah.
Well, we have 6 of them.
And
No way, there are only 5 here. What happened?
I gave one to one of our speakers. Yeah, already.
Okay.
Thank you.
Yeah, and we want to thank everyone again for attending. We hope you found our content useful. Thanks to all our speakers again. We hope to see you all this conference again next year. And in the meantime, you can find us on the mailing lists. We look forward to hearing from you. And if anyone's going to be sticking around, we're going to be doing a Garth Brooks karaoke and sing along after this. So thank you.